Okay, hey, you ready? Let's go. I'm going to turn this to Elmo. We're going to do a simulation right now. Let me turn this to Elmo. And we're going to do a thing that you're going to measure at some point, either now or later today. You can do this. And this is called Chapter 2, Reaction Time. Now, I don't want you just to click a stopwatch, because you can learn how to do that rather quickly. You know, click, 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 you know, start, stop, start, stop. You can do that pretty darn quickly. But to see an external stimulus and to actually react to it physically is called reaction time. That's the time between a stimulus, and a reaction, a physical reaction to it. Some stimuli are visual, audio, taste, skin, skin reactions, those kind of things. So I want to measure your reaction time. I want you to calculate your reaction time. And if you had a ruler, so I'm going to set this up so that you can do this with a buddy before next class. You ready? This is how you do this. This is a simple lab. It would be done as a lab in a class if we had it. All right, so this is a ruler. It can be as short as a foot or a short metric ruler, or it could be a meter stick, or it could be a yardstick. A lot of families don't have any of these things in their houses, like a yardstick or a meter stick. I don't even have a meter stick at home because I've got 30 of them at school, right? So with this meter stick held vertically, you can let this thing drop. And by how far it drops, you'll know what your reaction time is according to the physics you already know. All right? So I want you to do a little drawing like me. Don't laugh at my drawings, okay? You're going to stare to get your reaction time. You're going to stare with your eyeball. This is your head, mouth, nose, and you're loving physics, so it's a big smile. All right, you got hair because you're young, and you've got ears over here. It looks kind of weird, but that's all right. You're staring at a place on the meter stick that you know where it is, okay? Let's call that the 50 centimeter mark if you had a meter stick. Now you're going to take your right hand, if you're right-handed, put your finger and your thumb right on the outside of that. So that's a finger and thumb, finger and thumb, not just two fingers. I mean, just one finger and one thumb. You don't want the whole hand sitting there, okay? Yeah, like you're holding it, just like that. And you're going to have a friend come over and hold the top. Not you, because you can't get your own reaction time. And they're going to hold the top up here with their hand. And if they're staring, they won't be able to see your fingers. Let me turn back to the other view. Let's go to FaceTime. So here's my little ruler, okay? You see this? And you're going to stare and put your two fingers at a place where you know that is, okay, on there. And then when it drops, you're going to grab it. As soon as you see it starting to drop, close your fingers and grab it. And that distance that it's fallen there is the distance we're after, that distance right there. I had two classes already today. Nobody had a helper that would come in and do this with them. So I'm going to make you do it tonight or before Monday, okay? You got to just promise that you're going to do this. All right, now up here on the top though, if they see your fingers open up, if they see that, they're going to react before the thing actually starts dropping, and they're going to get unbelievably short reaction time. So you have to cover up your hand. Cover up your hand, whoever's up there, the helper, so that when this thing drops, they don't see the fingers that are opening inside do that. Everybody understand? So you have to kind of hide that from them. Okay, so once they do that, this thing's going to fall a certain distance. So let's say you grab it here. This is where it's grabbed. I guess that's a verb, past tense. All right, so it's going to go from here to here, and that's your drop distance. That's the drop distance. Let me go back to Elmo again. Elmo, here we go. Now that drop distance becomes important because it's how far has something fallen, how much time does that take? And this is true for an apple, an orange, a rock, anything that's in free fall. If it's in free fall, that means there's nothing impeding it, including this ruler that's falling straight down, okay? Now, let's, I doubt if any of you have a helper. Does anybody have a helper just kind of hanging out in the house to do this, and you have a ruler to do it with? You do? Cool. You got a helper, Sean? Oh, how cool is that? All right. Tell him to come back. Sean, you're the man. Here we go. Tell him to hold it above your head. Put your fingers at the bottom. Know where you're looking. Get your eyeball right. Get your eyeball really close. Sean, you're cool. Oh, don't drop it yet. All right. Stare at that point and then drop it and then grab it. Drop. Did you grab it? How many centimeters?
That's nice. My thing only has inches, but I caught it at 10 and I was starting at 4. So
Oh, 6 inches? That's about right. Do it again.
is it very nice? 7.
Yeah, so 6 inches is where he's at. We can use that data in just a minute. Try it one more time. Get your eye close. I don't want you to see your hand open up. Go ahead. How many inches?
I got 10 again. It's very nice. Can you not?
So from 4 to 6? Cool. All right, we're going to use your data, all right? All right, so we're going to find out your reaction time. Everybody ready? Let's do this. All right, you ready? So let's start. We need to know what that distance is of 6 inches is into centimeters and into meters. So there's 2.54 centimeters per inch, and there's 100 centimeters per meter. So let's come up with what his let's call it DR for reaction distance. This is a reaction distance in meters. So as soon as you get that, type it in over on the right. We're using his data now. Thank you for volunteering. I love volunteers. Somebody type this in on the right. How many meters is this? So 6 times, oh, come on, I can do this. 0.152. 1524. I can leave all those digits in for now because we'll 142152 Okay, 1524. Okay, here we go. Let's use that one. So that's the distance. So how far can any object in the world near the surface of the earth fall? How much time does that take? So let's go back to our formula. D equals 1/2 A. In this case, we're talking about gravity doing the accelerating. T squared plus V naught T. And it started from rest, so that becomes a 0. Okay. Now let's rearrange this for T. So T is going to be T squared equals 2D over G. 2D over G is T squared. So T is actually the square root, this is reaction time, is the square root of 2D over G. Okay? So we're talking about the square root of, he said 0.1524 meters per second squared for 9, let's use 9.8. Now this is meters up here. So we end up the square root of seconds, which is seconds. Type that in. What's the reaction time? Put an S behind it so I'll know that you're doing my calculation. How many seconds of a reaction? This would be a great question, hint, hint, for your quiz next Thursday. So make sure you can do this. 0.1763 0.1763 seconds. And let's just round it to a couple digits. 1/8 seconds. Okay. Everybody get that about 0.18? Wave your hand if you got 0.18. Wave your hand so I know we're okay. This is the only way I can tell if we're in the right ballparks. Now, I'm going to show you a restaurant trick now. Restaurant physics. It's not a trick. It's restaurant physics. Now I'm going to label this one number 1 because I'm going to teach you about 20 or 30 of these this year. You have the option of scoring some money on your friends doing things like this. And if you know the trick and they don't, you can usually get them, okay? You can get them for $1 or $5 or something like that if you're a betting person and they don't care about their money. Okay, so here's how this works. You're going to drop a bill through their hands. I'm going to draw it. I'm going to show you in a second. You're going to take a bill, fold it, crease it along the vertical axis, and you're going to have them hold their finger and their thumb out here, just like you just did. This is the thumb, and this is fingers. One finger and one thumb. I didn't draw that very well. Okay, that's a finger and a thumb. You're going to drop it down through their finger and their thumb, hiding your hand up here on top. You're going to hide your hand. And if they can grab it, they get to keep it. Okay? So rule number 1, use their money. So if they keep it, they already own it anyway. All right, rule 1. Number 2, they say, well, what's the catch here? Well, the catch is that you're going to hold it in the middle. It's already halfway down. Okay, hold it in the middle. Number 3, you're going to hide your hand when you release it. Hide your hand. And 4, give them 2 out of 3 tries, because they're not going to get it. They're not going to get this. Okay. Now, let me show you, let's go back to, let's get rid of Elmo. I'm going to show you what this kind of looks like. I got a bill. I got a dollar bill right here. Okay. So while we're talking, I'm folding this thing vertically. If you have a bill, you can do this, all right, with you right now. Fold it vertically. Okay. Now, I don't want them to catch this. So why did I actually try to fold it vertically and make a little V out of it like this? Why did I do that? Somebody want to tell me? Why do I do this? So it will fall faster, but why? Less air resistance, exactly. I don't want, if it's flat, it's going to curl. It'll curl on the way down and take much longer. They're going to get it, okay? Maybe. But if you leave it vertically, it's going to fall straight through, okay? Now, the second thing is the look on the bill. You're going to hold it so that their fingers are right at the face. Now, they can have one finger touching the paper, but not both, all right? So you want to have their finger, you hold it so their fingers are right here at right above the face. That's halfway down. Now, up here, they're going to see your hand. So you have to actually cup your hand so they can't see it, and then release it so they can't see your fingers that are releasing the bill. Okay? Now, to tell you the truth, about only 1% of the people can get this. They actually are quick enough to get this. So let me go back and give you one more little note. You ready? About 1% of the people can get this every time, because they're built a little differently. They have fast twitch muscle reaction. Okay, muscle reaction. Now, fast twitch is kind of cool. You think about racers. Who needs fast twitch reactions with their muscles? Is it people running the marathon or people 100-meter dash? It's the 100-meter dash people, right? So 100-meter dash people, that fraction of a second better than somebody else might mean a win. Okay, marathon runners, shoot. I mean, if they're within a few seconds of the start of the race, there's no big deal. They can be back 20, 40, 50 people. That's not a big deal, right? So this is quick twitch as opposed to slow twitch. All right. So how do we calculate how much time they have and why they probably aren't going to get it? I had one student every year that can get this every time. And I remember I had a guy named Monty Smith. He was a third baseman on the baseball team where I was teaching. He could get it every single time. And why? Well, he was just quick. And it made him a great third baseman. Why? Because he could react to anything coming his way. He was already after it, and he was very successful. So sometimes you need good reaction time. And we'll talk about what other sports need good reaction time. Type a couple over here for me. Who would be more successful with quick reaction times? Sure, volleyball. What else? I'm thinking of some. Any goalie for any sport. Martial arts, of course. Ping pong, race car drivers, baseball players, catchers. Okay, who doesn't need good reaction time? Name a sport where reaction time means nothing. That's what I was thinking. Golf, bowling. Yeah. So if you don't have good reaction time, shoot, there's some sports for you. There you go. That's funny. Okay, so how far is this? Well, you got to measure your bill. If you have a bill with it, you can measure it. Mine in centimeters is 15.5. 15.5 centimeters is mine. All right, so my total distance was 15.5 centimeters. And we'll call that dB for a bill. 1/2 of a bill is going to be 7. What that 7?
Mr. O'Leary, can you
move the paper a little to the right, please?
Oh, sorry. That's one of the first things you learn in Japanese is gomen nasai. It means sorry. Okay, so and then 15 is 7, and then I've got a 5. Is that it? Are we okay there? So that's 1/2 of a bill. 1/2 of a bill. Now let's turn that into meters. So the drop distance that they have to work with is 0.0775 meters. That's 7.75 centimeters. So you got to be able to convert. Make sure you can convert. Now I want you to do the reaction time. This is reaction time with that distance. And we said it's the root 2d over g. What is the reaction time that people have? I know reaction distance is 7 3/4 centimeters, but what's the reaction time in seconds? Go ahead and do that and type it in for me. Let's see what you got. What's the reaction time in seconds? All objects falling this far would go that distance. Any object in free fall. Any object. I need a time. Go ahead. Somebody type it in. I know what it should be. What's that time? And we're practicing 0.126. 0.126. Yeah, that's about right. Yeah. 126. So 0.126 seconds is equal to a drop of 7 3/4 centimeters. Okay, 0.126. Now I'd like you to challenge some of your friends to this little thing. Okay. Now I have a lot of these challenges. So please go ahead and try it. I have only one sad story to tell you. I taught this to one class, and a girl came in. I said, "How did it go?" And she said, "It didn't go very well." And then she pointed to her eye. And anyway, she had a black eye, and somebody got mad at her or something. Okay, but that's not going to happen to you because you have wonderful relatives and friends. Okay, hey, let's go on. I'm going to turn this over, and let's do some practices before we get too far along. And I'm going to teach you a couple new things. This situation is where we're going to be on top of a hill or a cliff, and we're going to throw something up in the air, and it's going to go down, straight up and straight down, but you don't catch it. You don't catch it. Now we're going to, this is a building. This is the ground. And this is the final resting place. And this is the start right here, all right? So we're going to call this zero distance, 0 meters. Now anything that goes above me is called plus displacement. So I'm going to know from now on if something ends up being a plus number, it's above me, all right? Anything that's below me, if it's 0, it's where I am, okay? If it's below me, negative displacement means lower than me or lower than the place it was launched, all right? Everybody got that? This new notation, we're using vectors now, all right? Because before, you never threw anything up. You only dropped it, all right? You threw it down or dropped it. So this is a little more realistic. Now, anything that's going up, if you're going up, you're going to have plus velocity, okay? Anything that's going down would be negative velocity. And acceleration due to gravity is always down, minus 9.8 meters per second squared. That minus means down. It never goes up. Gravity never makes things go up. It only pulls them towards the earth, whether they're going up or down. It always pulls them down, okay? Star Trek had an anti-gravity beam on it where they could aim it at an asteroid, a ship, or a planet, turn it on and push away from it. Do you think that's is that possible? Absolutely impossible. So that's strictly science fiction. Okay, so let me give you a way to solve for this. I want to have 9 rows and 4 columns. See if you can do this. 9 rows and 4 columns. Good luck. 1, 2, 3, 5, 6, 7, 8, 9, or 10. Okay. And then I want 4 columns or 5. Okay. And we're going to put the time in the first one. And this is going to be in seconds, starting with 0 time. This is going to be the velocity, starting velocity, meters per second. This is going to be the displacement in meters. And this is for our first trial, and we're going to save those other 2 over there for another practice trial. Okay, everybody got to, I'm going to give you a chance. Fill out your grid. Fill out your grid. And I'm going to help you with the first one, and I'm going to turn you loose on the second one without me, okay? Now, we'd like to throw an object from the top of this thing up at 30 meters per second. This is 30. Now, it's not gone anywhere yet, so it's still a 0 displacement. It's the same place I am. So this is a plus 30 meters per second. I'd like to know 2, 3, 4, 5, 6, 7, 8. For 8 seconds, I'd like to know how fast it's going. Now, to make it so you don't have to use a calculator, for today, let's call it 10. Minus 10 meters per second squared. That way you don't have to use a calculator. It's so much easier. All right, you don't have to worry about decimals and all that stuff. Okay, you ready? So G equals minus 10. Now, we'd like to find out what is the speed down here. So let's see, speed, let's see, acceleration equals V minus V naught over T. That's a definition. So final speed only depends on gravity and time and starting speed. Okay? Now, this is what gravity does to the starting speed. Now, the starting speed here was a 30. Now, every time gravity acts for another second, we subtract 10 from this number. Let's do the first second. Let's do V1. V1 would be minus 10 times 1. So minus 10 plus 30 equals 20. This is so simple, but I want you to get the pattern before you go nuts. So here we go. So in 1 second, notice I'm just subtracting another 10 every second from that 30. So I just come up here and I say, 30, subtract 10, 20. Oh, subtract another 10, 10, subtract another 10, 0. That's the top. When it stops, when it runs out of vertical speed, we call that the top, okay? Now, in the next second, it's starting to come down. In that second, it picks up another negative 10, 20, 30, 40, and 50. Okay, everybody see it? Now, that should make sense. So all we're doing is adding another 10 every second, and then adding that to the 30 that it started with. Now, that's the easy column. Let's do the second one. Where are you at after 1 second? There's 2 ways to do this. I'm going to do it over on the side. Ready? You can get the distance by 1/2 AT squared plus V initial t. Or, let's do that one first. Where am I at? So D equals minus 5, that's half of gravity, times 1 second squared plus 30, that was the starting speed, times 1 second, and I get a minus 5 plus, what's this over here? 30. So at 1 second, where are we at? We are at plus 25. We put that over here. Okay, plus 25. Now, I want you to think about this. If there was no gravity, I want you to circle something for me. If there was no gravity, it would just keep taking off, going 30 more every second, if there was no gravity. Okay? But because gravity holds it back from where it would like to go up to. That's what gravity's doing to this motion. So we have the uniform motion on the right, but it's being altered by gravity on the left. Now, so that's 25. Anybody not see how to get 25? If you can't see that, I'll do another one before I turn you loose in a minute. Okay, now I'm going to show you a simpler way. There's an easier way. This is the easy way. Total distance, d total, this is from the beginning. You can do a simple calculation. Just find V average times time. This is the simple way to do it, but you have to be careful. This is from the beginning. So let me show you. What's the average between 30 and 20? It's 25. All right, everybody see it? That's V average. Between that 30 and 20, the middle number is a 25. It's 25. 25 times 1, this is meters per second, equals 25 meters. I get the same answer as over there. All right, same answer. Now let me do another one with you before I turn you loose. You ready? What's the average between 30 and 10? It's 20. 30 and 10 is 20 times 2 seconds, times 2 seconds. So if I went 20 meters per second for 2 seconds, I would go 40 meters. Let's get to the top. How high does it go? What's the average between 30 and 0? It's 15. 15 times 3 is 45 meters up. Okay, everybody see that? Now, this is at the top. This is how high it goes. This is the top. That's the top. I'm going to teach you another word over here called symmetry. S-Y-M. Symmetry. You may have used symmetry in math classes, okay? This is a symmetrical nature process right here. Everything that goes up, it's going to do just the same sort of thing on the way down. Now, how far did it go in the last second on the way up? 5, because that was the average speed, actually, times 1 second. It's going to come down that same 5 in the first second down. So this is a 40. Notice that's symmetrical. Now, the next one is going to be symmetrical. We're going to pick up as much as we lost that second over there. And then, boy, we're back to where we started. But here's the question down here. What are these last two? It's gone below me now. So these are all positives. What's going on below me here? So let's do an average. Plus 30 minus 40 divided by 2. That average is minus 5 times 7 seconds equals minus 35 meters. Okay, minus 35 meters. So this is minus 35 right there. Minus 35. Go ahead and do this last one for me and see if you can do it before I turn you loose on the next 2 columns. And then type that in over on the side. What is the location after 8 seconds for this run? Where's it at? Good luck. Minus 80, very good. It's minus 80. So 30 and 50, this is from the beginning, is a minus 20 divided by 2 is minus 10 times 8 is minus 80. Now you could go do this stuff over here on the side, 1/2 AT squared plus B0T. You can do that too, I don't care. Whichever one you're comfortable with. Now, I'm going to give you a couple minutes to finish this next chart as if it were on a quiz next week. You ready? Here's your velocity, and here's your displacement.
Please move the paper.
Okay, sorry. Yeah. Sorry. I'm going to toss this up at 40 meters per second. And its displacement right now is a 0. And I'd like you to find out for each of those times, where is it at and how fast is it going? Okay, go. S-car, go. I would do this velocity column first because that's a piece of cake. And then do the distances. And I would use my shortcut if you wish, because it's legal. It's not illegal to take shortcuts if it's constant acceleration. Okay, go. Next, I got a ball toss after this is over. Now, when you have all of those, 14 boxes filled in, give me a high sign. It takes a few minutes. This is not something you can run through. One person's done, 2 people. Thank you. Give me a high sign when you're done. Oh, yeah. Thank you. It's hard to see with these little tiny squares on my computer. Unless somebody, thanks. Unless something's really moving around, I can't tell what's going on out there. All right. Cool, done. A bunch of dones. Done. All right, here we go. If you're done, you should be able to agree with me. These are easy. 40, 30, 20, 10, 0. Please label that the top. That's the top. Okay, label that. When things run out of vertical speed, you're at the top. And just for an instant of time, you're stopped. An instant, not 2 instances, just 1 instant of time, you don't have vertical speed. Now you instantly you start coming down. So this is -10, -20, -30, -40. Okay. Now, distance-wise, 35 times 1 is 35. 30 times 2 is 60. I'm taking the average times the time. So this is 25 is the average here, times 3 is 75. And now the average here is 20 times 4 is 80. Top gets as high as 80 meters. Notice it lost 5 meters that last second. Oh, that's what we did over here. Every object on the way up, that last second loses 5 meters, okay? So it's gonna gain 5 meters that next second on the way down. So by symmetry, 75, 60, 35, and 0. It's back to me again. It's back to me again. Any questions? All right,
Yeah,
we-
actually, just a quick question.
Yeah.
I've forgotten the name of the symbol for the second to last column. The one, the kind of looking V. Yeah, that one.
Oh, yeah. I make a V kind of like this. All right. It's meant to be like a little V as opposed to a big V. It's just a V. It's a V. It's nothing. It's not Greek. It's just my scribble. Okay.
Okay, thank you.
You can make it a little V. Is fine. And but if it's a V with an arrow above it, then we know that the direction counts. And plus and minus, north, south, all that stuff starts counting as soon as it's a vector. If it doesn't have that arrow, we call it, that V, a speed. And that's what your speedometer says in your car. Your speedometer doesn't tell you the direction you're going. It just says, how fast am I covering ground? You could be driving in circles. I don't know what it does when you back up. Does the speedometer work when you back up? I don't know. I don't know if it goes, I don't know what it does when you back up. It's kind of funny. All right. Any other questions other than my handwriting? Okay. All right. Hey, I've got a little thing I'd like to do with you now. And this is called ball toss. This is called a ball toss. And you're going to need about a half a piece of paper for this. And I'm going to show you something that's really cool. All right. Let's get another piece of paper. Oh, here it is. I'll do this. We're going to take a video of a ball being tossed up in the air and come back down and catch it. We're going to catch it. So this could be you tossing an apple, a volleyball, a tennis ball, football. Well, football, if you toss it straight up, okay? So we're going to take this thing and we're going to analyze it. And I'm going to show you 2 ways to analyze it. On the AP, they say, what would you need to analyze this motion or this situation? And I'm going to show you 2 new ways to analyze a ball toss. So just make a note. This could be a lab. If all of you had the lab equipment, this would be a lab. And it could be a video lab where you actually video something that's being tossed up and you catch it. I've done this in class and it's kind of fun. Okay, everybody ready? I'm going to put you on share screen and I'm going to show you something that I've been playing with this week. Share and bring this to the front. Okay, now you should see a lady on the left holding a black ball, and I'm going to slow down here in the corner. And this is a program called Logger Pro, which is only for Macintosh. But remind me later, you have on your computer, if you have a Chrome, you have a program that I'll write out later called Graphical Analysis for Chrome. And you'll be able to do what I'm doing right now, okay? It's from the company called Vernier. All right, So let's talk about this little thing here. I'm going to play it for you a couple of times just so you can see what it is. Let me play it in real time. This is down here, speed. I'm going to do a 1. Okay, start. Okay, kind of cool, huh? Let me hide the data and do it again. I don't want you to be distracted. Here we go. Start. Boom. Okay. So she is, let's move this down just a little bit. Let's move this up just a little bit. Oh, I missed it up there. Okay, I still didn't get to the top. Okay, so let's slow it down. Let's erase the data and you watch what's going on. Notice when her, let's make this 0.5. Okay, down here. Here she's starting. Released, top, bottom. Everybody see it? Okay, this is cool. So now what we want to do is analyze this. Now there's 2 little things going on here. Can all of you see that little green box underneath the ball? Just who am I looking at over here? You guys that are over here, just say yes or no. You can see it, right? There's a little thing over here. Oh, I can move the video around too. This little green box that's over here, I'll use my mouse, is a clicker, and it's a motion sensor. Last class I had somebody that actually used this in another science class. It's called a motion sensor. You did? You've used this? Was it in physical science? Yeah, it was. Okay, these are cool. So these things, let me tell you how they work. These things send out a sound signal. It's a clicking sound, kind of like a dolphin, okay? And it goes click, 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 and it sends out a sound beam, and it hits this thing and comes back, and it senses that. So it's got a little chip inside that's programmed that says, I'm going to take the speed of sound times half of that time, and that's where it's at. The bottom is anyway, okay? So that gives you data on the bottom of the ball. Everybody set? Everybody kind of got that figured out? This is how radar works. This is also how sonar works for boats. They send out a signal, know the speed of the sound at that temperature, divide by 2, and you got that. Also, speed guns for the policemen use this. Have any of you gotten speeding tickets? Oh, you haven't. You're too young, right? But this is how they work. Send out a signal, get it back, know the speed, divide by 2, half the time, find out your speed. Okay. The other way to analyze this is to go frame by frame. I can do that here, frame by frame, I think. Let's see. I'm going to go frame by frame and mark the middle of this ball. Everybody see it? And I can get data for a data table that you could analyze on your computer and get these same graphs. Everybody set? So that's another way I could do this. But let's come over here. Oh, she can make it go. She can float it in the air. Isn't that cool? I'm doing that. All right. So let's go over and look at the part of the graph that we want. So I'm going to select just the part that we want from here to here. Okay. And I'm going to do plus. And let's see what's going on. Could you please draw these two, and then I'm going to add information. This is a position time graph. Position time graph. Now notice that it took about 0.3 seconds to get from when she releases the ball to the top. About 0.3 seconds. So this is 0.7, 1 second, and over here is 1.3 seconds. Okay? And it's going to go up. Now, how high does it get? Looks like it's up here around 1 point. I figured out how to get it down. So it's right about 1 meter high. That's convenient. Everybody got it? Now, this is stretching out something that's vertical horizontally. So this is actually a parabola. So let's make a note of that. This is a parabola. Galileo figures out that accelerating objects, y equals 1/2 at squared. Well, y equals kx squared is a parabola formula, okay? This is the parabola. It's nice and it's beautiful, okay? For those of you that are into mathematics and science. So what's going on? Well, I went up here and grabbed this little thing called a tangent helper. This is a tangent helper. And we're going to take this tangent line and come back over here. Now, make a note to yourself that the tangent of a distance time graph is speed. Now, in that box, we can find out how fast is this thing going. So as soon as it leaves her hand, I don't think I can get a lower one. Okay. The fastest I've got over here on the left is a slope of 2.7 meters per second. That's as soon as it got out of her hands. That's how fast she launched it at. Now, as soon as she launches this thing, only gravity is going to control its speed and location, right? Only gravity, the force of gravity is acting on it. So as soon as I move this up, that slope gets smaller. 2.4, 2.0, 1.4, 0.7. Notice it's getting near the top. Now, if I can get to the top, 0.4, right at the top, 0.09. Now, notice it's slightly tilted because I don't have data to make it flat at the very, very, very top. So it's 0. So make a note at the top, the speed is 0. Speed is 0 at the top. Now, these were all plus speeds over here, plus slopes. We cross over the top. Now look, they're minus slopes. I hope you can read this. This now says the slope is minus 0.23. Now, as I come down, you can see it on the pictures over there. It's coming down farther and farther. Last class said that most video cameras are at about a 30th or a 60th of a second. 30th or a 60th of a second. I don't know what video camera they used here, but that's true. Now I can come down here farther, and when it gets right about to where her hands are, what did we say this up speed was? 2 point something, right? So here I got a negative 2.7. So by symmetry, you can see that the speed she launched it with is the speed that she catches it with. Make a note of that. So she launched it upwards at 2.7. She catches it at negative 2.7. Same speed, but going down. Everybody set? Now, we can see that after it leaves her hand, while it's in her hand, the velocities are changing irregularly because she's accelerating it. As soon as it gets out here and gravity takes hold, it now changes by the slope of a velocity time graph is acceleration. Make a note. So this is the slope is gravity. Now let's let this settle out. Negative 9.6, negative 10, negative 9.4, negative 9.4, negative 9.8. Oh, make a little note. When it gets to the top, does the gravity change? It doesn't. So gravity actually is the same as soon as she lets it go until the time she catches it. Gravity is acting on it the same the whole time. Negative 9.8 meters per second squared. So this slope maintains that negative 9.8 number all the way down until she starts touching it again, down in here. All right, down in there. Everybody got it? So the big note is, what's the acceleration at the top? Negative 9.8. What's the slope when she first lets it go? Negative 9.8. Just before it catches it, negative 9.8. The whole thing is negative. That's a straight line. Now, to see that, I think is pretty cool, because most people don't believe, they think that gravity is 0 at the top of a path. And I'm going to tell you that if the gravity was 0, that is problematic. Because if you jumped up and gravity became 0, what would you do? You'd start floating, just like in the astronauts would do, right? If you jumped, that would change life. If you threw something up and it stayed up there and floated around, it'd be terrible, okay? Including the air we breathe. We'd run out of air because it'd all just float away. Okay. Any questions on these, you can unmute yourself and ask before I delete this file.
Could you zoom out of the velocity versus time graph and kind of go over what it looked like before you cut it? Because that part didn't make sense to me.
Oh, oh, yeah. While she was tossing it. Okay, let's hide data and do it again. There we go. Stop. Okay. So back over here, back over here is where you're interested. She's making this thing go faster and faster and faster herself. So over on the left side, this is her going from rest, giving it a push, faster, 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 let it go. Okay, do you see it?
Yeah.
So over on the left, she's making it go from 0 to 3 meters per second, and then she lets it go. Okay? And now the gravity takes hold and adds a negative 10, negative 9.8 every second it's in the air until she grabs it again. Now this is her grabbing the ball over here. Okay? Does that answer your question?
Yeah, thanks.
Yeah. So the straight line is this straight line is while it's in the air. Other than the straight line, something else is affecting it. Okay? Such as her hands. Any other questions, please ask before I say goodbye to our ball tosser.
Actually, I've got a question that
Sure.
I've just been formulating. So, this also concerns the massive time velocity displacement velocity distance graph a while ago.
Yep.
I've been thinking, so earlier you used negative 9.8 meters per second squared, right?
Yep.
Yeah, and so that means that gravity would be constant in all of these problems too, because we're using
Yes.
Earth's gravity and all that stuff, right?
Yes.
So So would you be able to change it to 9.8 meters per second squared, or is it always going to be just negative 9.8 meters per second squared?
Good question. If things are only going down like the homework for today, you can call down plus, and you can use plus gravity because there's no changing of pluses and minuses. So if something is just rolling down a ramp, you can call down distance plus and down acceleration plus. If it's you're dropping something at the top of a building, you could just say gravity's 9.8. But I'm going to teach you now that they say more better. It's better to use the right symbols and you'll get better results. So you're going to do a practice problem right now. Okay? You ready? All right, you're going to do a practice. I'm going to stop sharing. I hate to leave this. This is a work of beauty right here. Okay? For all you people. All right. So now I'm going to do something I'd like you to do with me. This is going to be your practice problem for homework C. All right. And if you can get this right, I'm going to say you're really good to go. All right. So this is chapter 2, homework C, practice problem. And it summarizes everything that we've done today. And if you can get this right, I'm going to be so happy with you. And you're going to be happy with yourself. Practice problem. All right. So let's set up a scenario. Got to have a scenario. And we're going to toss a ball from the top of a hill, and it's going to come down in free fall. This is not a trajectory. This is free fall. And we're calling this one-dimensional, not two-dimensional, just one-dimensional. So it's tossed straight up, straight down, but I don't want to draw over my line, so I put it over to the side slightly, okay? Now we need an initial launch speed. And since this is COVID-19, we're going to give it 19 meters per second up. That's what that means. 19 meters per second up is VO, the original speed. At some time, it's going to stop. About how many seconds is it going to take to stop? Type it in. How many seconds for this thing to stop? 2, exactly, about 2. All right. So gravity adds a negative 9.8 to the speed. We had 20, about 20. So it's going to take about 2 seconds to stop going up. Now it's going to come down. Let's say the total time in the air from time launch to time that it hits is 6 seconds. That's T total. Okay, we're T totaling today. And I'd like to calculate two things, and then we're going to graph it eventually. What is the speed that it hits the ground with at 6 seconds? I'm going to call that V6. How fast does it hit the ground? And what is D6? Where's it at? I put little arrows on the top, which means that these are vectors. And of course, they're both going to be negative, or you've done it wrong, because it's below me and it's heading down. I'm going to give you a couple minutes and see how far you get on this. And then we're going to graph them, and we're done for today. Go. As soon as you get those two numbers, I want meters per second on the first one, and I want meters on the second one. Type them in. And if I agree with a few of you, I'll go over it with you. Go ahead and try. You can do this on your own. Gravity is 9.8. Good question. We're going to use gravity as negative 9.8 meters per second squared. Good question. Yeah, you got to know what you're working with. Yeah, we got the velocity right. I'll come back to that. That one's right. I'll show you how to do it if you're confused at all. And then where's it at? Where is it at? Yep, negative 62.4 or 5 meters, okay? Around there, okay? Now I'm going to show you how to do it. Make sure you're okay with it, because some of you are faster in math than others, but all of you are capable. You're supposed to be in Algebra 2 or above to be in this class. A lot of you are in calculus, but all this really requires is a working knowledge of algebra and trig, okay? So here we go. Let's do this one. The speed at the bottom is going to be AT plus V0, okay? We have minus 9.8 times 6 plus 19, and that should be 39.8 meters per second, okay? Let's do the second one over here. Second one says D equals, now we know the average speed. We could do it that way too, but let's do it the other way. Let's say I didn't know the final speed and I wanted to do it the old way. So it's minus, let's see, 1/2 of A minus 9.8 times 6 squared plus 19 times 6. Now this is where it would be if there was no gravity. This is how far gravity has trunched it down. And you should end up with negative 62.4. Now, if you can't get that, you can ask me real quick. Okay, you could ask me. Okay, our last task, and we have about 10 minutes, and it's going to take about 5 minutes to do this. Let's write down two things. On your computer, there's a program called Vernier. Let's go back over here. Distance, speed, and acceleration. Only let's call this displacement now. We might have minuses, velocities, and accelerations. This is plus stuff, this is minus stuff. Plus, minus, plus, minus. All right, go ahead and do these. Have at least one data point, at least one legitimate data point for each of these graphs. Go. Let's see how good you are. Now this is setting you up for success for doing the homework C, but you can't really start it until I get these student access codes figured out, and I will email a message to you as soon as I find out by noon tomorrow. I apologize that that got kind of confused. I want at least one legitimate data point for each one. I'm going to give you a hint that this was 6 seconds. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So all of them took 6 seconds, so they're each 6 seconds long. When you're done, wave, give me a high sign. Give me a wave if you're done with all 3. This takes more than a minute. Yeah. Oh, is that a high sign? If you give me a high sign if you got all 3 and you're pretty confident about them. I don't see any waving yet. God, we ought to do a wave on Zoom. That'd be so cool, the video. Except your order is different than my order, so it wouldn't be in order. Windows and MacBook. Okay, we'll look into that. It'd be so cool if we could analyze some. Our next chapter is on trajectories. It'd be nice if you could analyze your own trajectory on your own program and get those graphs. Okay, we ready? All right. Who's done? Give me a high sign again. 1, only 1, 2. Wave like this is your life depends on it. Let me see it. I got 2 people, 3 people. I got a thumbs up. I like thumbs up. That's kind of cool. All right, 4 people. Thank you. 5. Good, thanks. Let's do these. You people that are a little slower, it's okay. Every race has rabbits and turtles, okay? And both of them get to the finish line, and that's fine. You all have to get to the finish line. So here we go. Let's do the easy one first. This is minus 9.8, and we know that it ends up at minus 40. If that's 20, 10, 20, 30, 40. In 6 seconds, it's over here at minus 40, and that goes da, 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 and it hits the 0 right about 2 seconds, right? You know that. So that slope is minus 9.8. Starts at about plus 20 and it ends at about minus 40. Okay, about. Now, distance-wise, wow, let's see. We're starting here at 0. And we know that it ends up down here. 1, 2, 3, 4, 5, 6. Minus 62. So it's down in here someplace at the end. Minus 60, around there. Now, how high would it be at when it stops going up? And that'll help us with our graph. We said it takes about 2 seconds. So half of that would be 10 times 2. It goes about 20 meters up and it stops. Okay, about 20 meters up when it stops, when it runs out of vertical speed. Now all we have to do is draw a nice, beautiful, if that's 2 seconds, this is going to be about 4 seconds. That's symmetrical. And then it just keeps on going down to there. Beautiful parabola. All right.
Mr. O'Leary,
Yeah.
how'd you get 20 meters again?
Oh, it's going up at 19.
Mm-hmm.
It stops at the top. The middle number is about 10.
Oh.
10 times 2 seconds is 20.
Oh, okay.
All right. So that's how I approximated it like we did in that chart. Average speed times time. I know it stops in about 2 seconds. Okay. Any other questions about this graph? Okay. All right. So what's your homework? Homework C. Drop a bill. Make sure, I think all of you have your lab, almost all of you have your lab 1 turned in already. So do homework C, drop a bill, and hope that I can get this sorted out with WebAssign. I spent an hour on already, my lunch hour with Cengage already today, and they didn't solve it. So I'm going to call them back again. All righty. So we had another good day. I hope today was fun for you. I think dropping objects is really cool. But next chapter, chapter 3, we get to launch things, which is even cooler. So off of tables and bows and arrows and all that kind of stuff. So I'm going to let you adios. And when if you want to stick around at the end, I'm going to say goodbye right now. If you want to stick around and ask me questions, please do. But this has been a good day. And sayonara and aloha.
Gravitational, root 2GM over R. It's inescapable, cause I can find velocity. Miss Mills, she taught me. Gonna get 5 on this exam, that's a guarantee. Elastic collisions I've been observing, but your momentum don't need conserving. My love for friction is concerning when you talk physics to me. Talk physics to me. Talk physics to me. Talk physics to me. Get torquey on it.
And aloha and all that.